Lenz law. Alright, we have seen about Michael Faraday experiment, and in his experiment, let me just remind you quickly that he found a current is always produced in the coil due to a moving magnet. Okay, so this is a coil, right? If this magnet with its north pole moving towards the coil, then there is a deflection in the coil in this direction. I mean in the galvanometer. Okay, so here it means that we are getting a current from the magnet. Okay, so this phenomenon of productions of electric currents from the magnetic field, that phenomenon is known as electromagnetic induction. Electromagnetic induction. And this electromagnetic induction, it is just opposite to the magnetic effects of current, because in magnetic effects of current we have like this. When a current is passing through a conductor, then we get a magnetic field around the conductor. So in this magnetic effect of current, what we found is we get magnetic field from the current, but in electromagnetic induction we get current from magnetic field. So it is just the opposite of the other. Okay, all right. Now, if you remember in Michael Faraday's law of this electromagnetic induction, okay, because this Lenz's law, it is actually associated with the second law of Michael Faraday, and Michael Faraday's second law says that the induced EMF in the coil is equals to minus d phi upon dt, where d phi upon dt, this is known as the rate of change of magnetic flux. Okay, now this Lenz's law, as I have explained and I have already mentioned before, it tells you about the negative sign in this equation. Okay, so let us understand about this negative sign. Okay, suppose this is a coil, okay, and if I move, let's say this magnet with a north pole towards the coil, then a current will be passing through the coil due to the moving magnet. And in which direction the current is passing? Alright, so for that we will do like this. Okay, suppose this is a north pole and I move the north pole, let's say, towards the face of the coil in this way. Now this face of the coil, which is close to this north pole, right? It will behave like a north pole of the coil. So it means I will get like this. Okay, and if I move the south pole towards the coil, then this face of the coil close to the south pole will behave like a south pole only. Okay, so look at this condition. So when this is the north pole, right? So for north, I put an arrow at the extreme end of this letter N. Then this arrow, it means, right, the directions of current is going in this way, right? And here it comes down, so this is the directions of current. Okay, so please remember, when the north pole of the magnet is moving towards the coil, okay, suppose this is the north pole and this is the face of the coil. If this north pole is moving towards the face of the coil, then this face of the coil will behave like a north pole. And if I move a south pole like this, if I move a south pole towards the face of the coil, then this face of the coil also will behave like a south pole. And if it is a south pole, okay, then its direction, the directions of current in the coil will be like this, as indicated by the extreme ends, right? The arrow at the extreme ends of the letter S. Okay, so it is clearly seen when the North Pole is moving towards the coil in this way, then where is the directions of the coil? The directions of the where is the directions of current? The directions of current should be in clockwise direction. So in clockwise direction, it means like this. Sorry, this is anti-clockwise. So the current will be flowing through the coil in this direction. Okay, in this direction. All right. Now, because this is a North Pole, right? If you move the magnet, like in this case, if you move the magnet towards the coil, then this face of the coil behave as the North Pole. So if this face behave as a North Pole, it means that this North Pole of the coil, now it will try to oppose the incoming North Pole of the magnet. Are you getting my point? If this is the North Pole, and if you move the North Pole towards the coil, then this face of the coil, it behave like a North Pole. So if this is not, this is also not, then what happen? Now the magnet, right, will experience a repulsion by the coil. Okay, so it means that this current here, which is flowing in the coil, right, it is flowing in such a way so as to oppose the incoming North Pole of the magnet, and that is Lenz's law, and that is why we have negative sign here. So this Lenz's law, it states like this. Lenz's law states that the directions of the induced current or the induced EMF in the coil, it flow in such a way so as to oppose the cause that produces it. Alright, so once again, right, suppose this is a face of the coil. If the North Pole, it is moving towards the coil in this way, then this face of the coil will behave as a North Pole, which means the current here will be flowing in anti-clockwise direction. So this motions of current here, it is so happens that, you know, it will try to oppose the cause that produce this current. Who produce this current? It is the moving magnet. Now this current here, it will flow in such a way so as to oppose the incoming magnet. Alright, so that is why we have this negative sign. So this negative sign about EMF in this case, it means that the EMF, right, will be in such a direction so as to oppose the cause that produces it. When I say the cause, it means the source which produces the either the current or induced EMF. Alright, I hope this Lenz law is clear now. Right? Okay. Now, another thing is, this Lenz's law is actually the law of conservation of energy. Okay. So, law of conservation of energy states that energy can neither be created nor destroyed, but it can only be transformed from one form to another. Alright. So if you move, like in my example, if I move the North Pole of the magnet towards the coil, then that face of the coil close to the North Pole will behave as a North Pole only. So because that face here, it behave as the North Pole, it means this magnet now will experience a repulsion. It is not so easy to push or towards, to move the magnet towards the coil as it is being opposed by the North Pole of the coil. So in that case, I need to do some work. I have to spend a mechanical work. So that mechanical energy which I spend to move my magnet with its North Pole towards the coil, that mechanical energy here, right, it will be transformed into what? Into the electrical energy. Okay, so if you move the magnet, you are doing mechanical energy against who? Against the opposition by the coil. Okay, so but that mechanical energy which you are doing here, it will appear in the form of the electrical energy in the coil. Alright, so that is how, right, this Lenz law, right, it is also known as the law of conservation of energy. Okay, similarly, if suppose this is the face of the coil, okay, which means this face. Now if this is the south pole, this is the north pole. If I move the south pole towards this face, I mean towards this face, then this face here should behave like the south pole. And if it behaves like the south pole, then the current here, right, it can be seen, right, moving in, in clockwise direction. So similarly, when the south pole of the magnet is moving towards the face of the coil, then that face of the coil will always oppose the incoming south pole of the magnet. So because of the opposition, I need to spend energy to overcome that opposition. But this mechanical energy which you spend here, it will be converted into electrical energy, and that electrical energy, it will be appeared in the coil. Okay, so which means you can read that energy or the current from the galvanometer. Okay, all right. So this is about Lenz law, which tells about the negative sign in this equations of Michael Faraday's second